If I'm going to use this stand, I'm going to pass it through the gap and then tie it up like that. So wherever I want to make it you can change the length of the pendulum by just sliding it like that. And to fix it in one position, you just roll it up like this, and that's it. It won't go anywhere. So that's how a pendulum is set up. So what do you need as materials? Pendulum bob, stand. You need a stopwatch, which you're going to use your cell phone. I can give you the stopwatch here, but I think cell phones are better. Okay? Use your own cell phones. It's much easier now. All right. So what's the theory behind a pendulum? So this pendulum bob right now is suspended because the weight is acting straight down, and the tension is actually pulling it up straight. But when I move it in this position, the weight is acting here. The weight is, if I swing it to one side, the weight is acting straight down and the tension is pulling it here. So there's a net force which is actually this way. And that net force is what is trying to bring it back. But because it's trying to bring it back, it gives it momentum. And that's the reason why it is not going to stop here. So it will keep going to the other side. And then stop somewhere here where it has lost all this energy and gained back potential energy. And then it swings back again, goes to the other side, swings back, goes. So this is oscillation. This is a pendulum's oscillation. Now the pendulum's oscillation, of course, is controlled by gravity. Now if gravity is less, let's say on the moon, then it's going to go slow because the weight is less. Now if you take it to a space station and you leave it here, it will stay there. If you leave it here on the top, it will stay there. So wherever you leave it, it's going to stay because gravity is apparent gravity is zero. So what is happening here is the pendulum is governed by, the time period of the pendulum is governed by some factors. One of them is gravity, and the other one is the time of this pendulum, how long it takes to swing, is governed by two factors. One is mass. It does not matter. Mass does not matter. Say it again. Air resistance will slow it down, but timing is not affected. Slope of what? Oh, you mean the angle of swing? No, angle is supposed to be small angle because, a formula is derived. The formula for time period is derived by assuming the angle is small. Small means like less than 5 degrees. So this is not the right way to do this experiment. Okay? Length of the string. The length of the string is the other factor. Gravity and length. These are the two factors that governs it. Now, what do you mean by length? Like, how do I measure the length of this pendulum? How do I measure the length of this pendulum? To the end of the bob? Any ideas? With the information that you got in the last lab, you must be able to say it correctly. From here, from the point where it's suspended, from this point where it is suspended, to where? Is it till the top of the string, the length of the pendulum, or to the bottom, or to where? Center of gravity of the bob. The center of gravity of the bob is right in the middle. So the whole bob is appearing to be big, but the whole weight is concentrated in one spot, which is the middle of the bob. So the length has to be measured till there. And to measure the length, what you do is you use a meter stick, and use a meter stick like that, and keep the zero there. You keep the zero there, and then keep this bob next to the meter stick and find out where the center of the bob is coinciding. So in this case, I see it's coinciding the center of the bob. This is literally the place where the bob is going to hit the meter stick, almost, right? It's almost like that. So yeah, this looks like around 64.5. So that's what I see as the length. That's how you measure the length. From the point of suspension to the center of gravity of the bob, which is almost the middle of the bob. And the other factor is gravity. Okay? So the time period is given by that equation. You see that equation there? Formula used. Time period is given by 2 times pi times square root of L over G on the sheet. 2 times pi times square root of L over G. So time period is given by the formula 2 pi square root of L over G. So look at this equation and you can say so many things. When the gravity is smaller on the moon, the denominator is smaller, what will happen to the time period? Go up. When the denominator goes down, the whole thing has to go up, right? So when the gravity goes down, like on the moon, time period will go up. What is time period? Time period is the time taken to complete one complete oscillation. You must have seen that in the first chapter itself, right? Time taken for it to complete one oscillation. And what is that one oscillation? It's like from the middle, from here, go this way, and back to the same place. That's one oscillation. So you count the oscillations by, you count the timing, you're going to count it from the middle only, not from the end. Why we do it in the middle is because middle is a place where it flies by quickly. So you have hardly any time to respond to starting the stopwatch and stopping the stopwatch. Whereas if you're looking at the end points, it is stopping and turning around. So that's a little more relaxed. So you'll be a little more relaxed on starting and stopping the stopwatch, which makes you make mistakes. So timing should start from the middle. All right? So can you all take your cell phones and just time this and tell me if everyone is getting it right? Now we're going to time 10 oscillations. Why 10 oscillations? Why can't you just do one oscillation? To improve accuracy. To improve accuracy, we are doing 10 oscillations. And how do you start the stopwatch? You start the stopwatch when it crosses the bar. When it crosses the bar, that's when you call it 0. And then when so it's like this, 0, 1. That's when it's finished one oscillation. Okay? And then 2. So that's a very common mistake. When I tell people to count it, they'll count like this. They'll start the stopwatch like 1, 2. That's not correct, because when they said 2, it's only finished one oscillation that time. So your starting of count will start from 0, not from 1. Right? When you start your car traveling from X to Y, as soon as you start the car, will you say 1 mile? No, you're not done any mile yet. You're just 0 mile. And then after 1 mile is finished, then you see 1 mile coming out, right? Make sense? So here also same thing. We're going to start and stop the timer accordingly. Keep your stopwatch ready. Timing is an important thing here in this experiment. And let's time. Where the heck is stopwatch? Forgot. What's in the top? Oh, it's okay. So I'm going to count down 3, 2, 1, and when I say 0, you stop. Is that okay? And then I'll stop at the 10. So, ready? 3, 2, 1, 0. 1, 2, 3, 4, 5, 6, 7, 8, 9, and 10. How much do you get? 16 point? Oh, 16.17? Yeah. I got 16.18, which looks like pretty good there. I'm doing it again because we're going to do timing 3 times for every measurement. Again, for improving the accuracy. So 16.18. And then you reset it and then start again. You don't have to stop it. See, this is going on. That's fine. 3, 2, 1, and 0. 1, 2, 3, 4, 5, 6, 7, 8, 9, and 10. 16.13. So you see the difference is, huh? Yeah. So that's how close we are. 0.05 seconds close. Okay, so you can't make more mistakes than that. Okay, so this is how we do it. And what are we trying to investigate here is this equation. Now think of this. This equation is also applicable to our walking. Have you seen tall people walk in a lazy fashion? And short people walk in a very brisk fashion? Doesn't mean that short people are brisky people and tall people are lazy ones. Why tall people are walking in a lazy fashion is because their leg is long. See, the leg is a pendulum. The leg is a pendulum, suspended here. So when you're actually walking, you're letting your legs swing like a pendulum. Swing. That's a casual walk. When you force yourself to walk, that's a different thing. But a casual walk, you can walk miles without getting tired. It's a casual walk. Because all you do is like lean forward, release your leg goes next part. That is a relaxed walk. So when you relax and walk, the taller people will walk in a lazy fashion like this. It will appear as if they are lazy like this. It will appear as if they're walking like this. Why are they walking like that? Because their leg is longer. And so it will take more time. Look, time period is proportional directly to the square root of the length. So definitely, the longer the length, the longer the time. Short people have shorter legs, which means when they swing it like a pendulum, like this. This is a short pendulum. And look at this one's timing. When the length is reduced, the time is actually shorter, right? So, yeah, the tall people, even short people will walk like that, brisk, making it feel like they are very energetic. Not necessarily. Okay, so you can see the pendulums, or a swing. When you go to a park, you see the swing. Tell me this. When you go to a swing, and you swing by sitting on the swing, and then after some time you get bored, and you stand on the swing and swing. What is it going to be the difference? Will there be a difference when you stand and swing versus sit and swing? Which one is going to be like faster? Stand or sit? Huh? Which one is going to be like shorter time? Standing shorter time. Why? Center of gravity. Good. When you sit, your center of gravity is low. When you stand, your center of gravity has gone up there. So that means the effective length of the pendulum is shorter. That's why it's kind of faster. Makes sense? So yeah, this is the equation that we're investigating. So that's basically what it is. And what you do is, to get into the square root sign, we square both sides. So when you square both sides, we get this. And then if you make g the subject of the equation, we get this. Say again? Yes, you're going to change the length and get the respective timing. That's basically our experiment. So what you're going to do is to plot a graph. We're going to plot a graph and do it, because graphical way of doing it is going to get you a better average. Instead of going with absolute substitutions, you can go graphically and get a perfect values. So plot length over there and t-square over there. And when you plot the length and t-square, you will definitely get some points. And then you join the best fit line, get the best fit line. And then find the slope of the best fit line. You know, slope is rise over run. Slope is rise over run. That's rise over run. And the rise is length. And the run is t squared. So when you take the slope, you're getting this. So what you're going to do is you're going to find the g with one equation. That's it. So where are we going to get the slope from? From the graph. You know, we could do this because of time. We can do this. Now you understood what exactly has to be done, right? What I can do is I can set it up for different lengths and I can let it oscillate and we will do the timing together. You can stick to your time. You have to take your times. We're going to fill up the table ourselves. Okay? As long as the answers are nearby, then you pick up those numbers and make your table. Is that okay, or do you want it personal? Personal. It's fine that way. I don't mind, because I can actually provide you all that stuff, but you're going to go home at 10 o'clock. All right, so that's why I'm like, I will set it up right here in front of you, so you will know exactly what is going on. And then you pick up those numbers. I don't know how to do this. I guess I put the laptop there. All right, so yeah. So we're going to do it together, right? Agree? How many of you agree with this? Right. Couple of things that I have to show you here is how to draw the graph. So I'll show you how to do the graph, but then you're going to do it yourself on a computer, and I'll show you here on the screen, okay, after the same time. So let's start working on this. I've written down the procedure, but that procedure was written down mainly for to help students do the lab at home using common tools. Right? That's why you see I'm saying feet and all those things, and later on they have convert because nobody has meter sticks at home. You have measuring tapes, which they don't have centimeters, they have inches, most of them. So therefore, it's better that they. All right. So aim of the experiment is clear. Apparatus is required or material is required. Theory is clear. The theory behind it is what I said all the time. Time depends on G, time depends on L, and all those things. And the formula that's going to be used is all that. But the last formula that we wrote down, this one, that is the ultimate formula that you use. Only one calculation that is there at the very end. Okay, only one calculation. Yes. So the procedure is this: set up the pendulum, change, set up the length, set up the pendulum bob, measure the length of the pendulum from the point of suspension to the center of the gravity of the bob, and then you're going to time. So can you change that time 20 oscillations to 10 oscillations on the table? We're only doing 10 oscillations. And then you do the average of 10 oscillations. And after that, you're going to divide it by 10 to get the time period. Time period is the time for one oscillation. So capital T stands for time period, is time for one oscillation. And then you square that and then write down the last part. So I'm going to keep this length. What is it length? How much? 54? 64.5. I'll double check it. Oh, no, 60. Did I say 64? No, I didn't see. Oh, yeah. Thank you. Oh, this is good. Yeah, 64.5. Because the string kind of stripped all around. 64.7. 64.6. I guess we need to do the timing of that. So what you do is, take these. In the fourth column, in the fourth line, row, in the fourth row, put down, what is it, 64.7, right? And you want to put meters, so put 0.647. In the fourth column, fourth row. Point 647 meters. You don't have to write meters. If this is the length, you need. So since we already arranged all that here, okay? Now you can take your cell phones and time it. I'm letting it oscillate, and when you share the numbers, you can find out your own timing. Even if you're watching this video, you can actually watch it. Take your time. When it crosses the middle, that's when you count 0. You can do it in your head. I'm going to do it in my head. I'm not going to count loud. When I start the stopwatch, it should be 0 in the middle. got 16.13. How about you all? Is it around there? I got 16.13. Okay, take that number. If anyone has numbers just close to this, 15.29, let's try it again. That's why we do it multiple times. So let's see if that is closer or ours is closer. Yeah. 16.1. I'm getting 16.21. Okay, so 16.18, you said? Okay, 16.10, 16.13, why don't we go with that? 16.10, 16.13, 16.1, whatever, 16.21. Take those numbers and write it there 3 times. There are 3 blocks. So you write here, one of them, second one, third one. We got a couple of numbers here. You can actually choose any of them. 16.13, 16.18, 16.21, 16.1, 16.21, 16.1, 10. Any of these is fine. Close enough. And then what do you do next step? Average of those 10 oscillations. Average them. The 3 numbers, average them. And then write that down. So it's 16 point something. And then T, capital T, time for one oscillation in seconds. What you do is divide by 10. So it becomes 1.6 something. Is that ready? Yeah. So it will be 1.61 something. Okay? And then you square that number. But clear the calculator screen and put that number again. So 16 point, let's say for the 1.615 is what you got, then 1.615 squared. And then round it up to the same number of sig figs, 4. So your t square should be rounded up to the same 4 sig figs, which would be like, what is this, 2.7, 2.6 something? 2.7? What do you have there? The t square column. 2.6, 2.629. Yeah. Again, it depends on each one. I'm going to do it for different lengths now. So I need to do 5 different lengths for a good graph. Okay. I got that length as 30.9. 30.9. So put it down in this column here. 0.309. Okay, I'm going to go from here. 30s, 40s, 50s, 60s, 70s. 30s, 40s, 50s, 60s, 70s. Right, now we're going to do the timing for this. If you got a number, can you display your cell phone? Can you show you? You're not done it? That's good. Yeah. 11.25, 11.22. Anybody else close now? 11.36. 11 point? So probably I'll have to do it again because it looks like anybody? 15. So anyway, 11.22 is what I'm getting first time. Let me try it again. That's a little slow. Oh, sorry. So 11.28. I think I will go with that 11.25, 11.28, and 11 point. Go ahead with it. See the average things. Forty-one point two. So we have get down. This is wrong. Everybody else is wrong. 12.98 or 12.92. I'll try it again. Maybe 12.92, 12.94. I think I'll go with this. 12.94, 12.92. That's my last time. 12.98. So yeah. Okay. Those are numbers. Take the average and fill up the last column. $50.9. Yeah, I've got three good numbers here. 14.38, 14.42, 35. 35. So take the average of that. That's good. 14.38, 14.35, and 14.42 is it? Yeah. That's the last one. Oh, did I save it in? 72.2. 72.2. Super. 17.06, 17.19, 0.10. Good numbers. 17.09, 17.06, and 17.10. And complete the table. Any questions about completing the table? Let me know. And then I'll show you how to draw the graph. Okay? Because I've given instructions there, slightly outdated, but you can see how I'm doing it. So I'll show you exactly how the graph is done. So procedure, make your own procedure of what we did exactly. And observation is your table which you just got. That is going to be your final table. And then calculations. You don't have to say plotting the graph. You don't have to say that. Calculations, in the just title it as calculations, and then your graph is going to go there. And then after the graph, you're going to use this equation once. Okay? And then after that, you can say all the precautions. These are multiple precautions here. The angle of swaying should be small angles, not like this. Yeah, not like this, because then the equation is wrong. The equation is derived by assuming small angles. And the other thing is make sure that the length is measured from the point of suspension to the center of gravity of the rod. And then for accuracy, we are repeating this experiment multiple times and doing it 10 oscillations. So we did so much to make sure that the numbers that we got are very, very accurate. Calculation. The observation is just the case. That's what we observe. And the other part is all. So for the graph, what do you need to do? Okay. Did you complete the table? Okay. Okay. The first column that you see there, what is that? Length, right? On the graph, what is supposed to be that axis? What axis is supposed to be that? Y-axis. Y-axis. And the last column that you got, that is the time square axis, which is going to be your x-axis. So to draw a graph, you're not going to do the conventional way of doing it on paper, and making all those grid lines. They do it using Excel. So we're going to go to Excel and then plot it. So if you don't have Excel and all that, you can actually go to some public library, you should be able to get it all. So we need Excel. All right, so I need to open up Excel. This. Excel is ready. What do you do now? You see these columns here? This is A, that's B. This is A, and that's B. In column A, feed all the X variables. What are the X variables there? Which are the X variables? No, length is on the Y-axis. Can you put an X on over the table for time squared? The time squared. That's the X variable. That's supposed to go in column A. So can you read out somebody's number? Yeah, you can tell me the number. What do you have in that column?
1.306.
1.306,
1.676,
1.676,
2.068.
Is that visible from there? Or should I zoom in? Good. What's the next one? Oh, yeah. Okay. Yeah. And what's the next one?
2.068.
All right.
2.629.
Okay.
And 2.933.
Yep. Now you go to the next column. That next column is your y-axis column. So these are all the length values that you got in the first column. Tell me all the lengths. 0.309. Okay. Say it again. 0.2. Is that right? Next. 647. 7. 2, 3.
2.
2, 2. All right. You got all those numbers. That's your first step. The next thing what you have to do, pay attention to me. The next thing what you do is click the first cell and select all these cells. Just select them. Select the cells. And after you select the cells, go to Insert. And on Insert, you see here Charts. And this one here says Scatter, Insert, Scatter, X and Y or bubble chart. Click on that, then it will open up like this. And the very first one, that's what you click. And your graph is ready. But then the graph does not have any details, so now you have to fill in the details. But what is the y-axis? So we don't have anything here, right? So if you click on the plus sign here, it will ask you, okay, what do you want? Axis title? All right, I need axis title. I need a chart title. And I think right now, that's good enough. Now, axis title. Click on the axis title and then type in. What is that? What is the axis? Length, and within brackets meters. And then this axis is your horizontal, like x-axis, which is time squared, time to the power of 2, or time period squared. And within brackets, second squared. Okay. So we got the chart title. Click on the chart title, and then very slow title. Okay. Simple pendulum. That's all good. The next thing and the very last thing that you need to do is to get the slope and then carry it to our calculations. So the chart is ready. To get the slope, there are different ways of doing it. You can right click here, right click any of these dots, right click. Right click on any of these dots. And you go down here and it says add trend line. So click on add trend line. Then that pops up. And then there it is asking you, are you anticipating to get an exponential graph or a linear graph or logarithmic graph or polynomial graph? We are expecting a linear graph, so that's good. And then if you scroll down to the bottom here, it will say display equation on chart. Check on that. Check on display equation on chart. So we got that checked. And see an equation has popped up here. And that equation we can actually make it bigger to make it, you can increase the size of it. You can leave it on the graph itself. So that is our equation. Have you seen an equation of a straight line? Y equal to mx plus b format? Yeah. So what you see over here is 0.0152 is the y-intercept. So if you continue that graph, it would have hit below the zero, and it would have hit 0.0152, which is very small. So our graph is pretty good. So it's nearly passing through the origin, which is what is supposed to be. If you make some errors in measurement of length or time periods, this number will be good, indicating the presence of error. Now, when you see 0.01, only 100 or 1/10 of this column here, which is very small. So the graph is pretty good, and you're getting almost a straight line. I can see some points are slightly up and down, but that's tiny bit.
I think it's also kind of from where I've been.
That's also there. Those are all going into the conclusions. So you can actually say what kind of errors can pop up. Now here, it's not one person's job, it's everybody's job. So therefore, if any mistake is taking place, we have to take the blame for it together. I'm not looking at the number answers for correctness. As long as your lab report is properly put in, that's enough. So that is so what is the slope from this graph? What's the value of slope? Y equal to mx plus b. M stands for slope. So the slope is 0.2521. That's what the slope is. And that is the only number you need from the graph, from this graph. But before you exit this graph, how do you take it to your Word document? Watch this. Go to an empty space. Go to an empty space. Right click. Copy. And then go to your Word document where you're typing your Word document. That's where your Word document is being typed. And you're saying calculations. And then right click here and paste it. Boom. And your graph is there on Word document. And everything is there. Whatever you did is there. Title is there, slope is there, everything is there perfectly. This is what you need. Okay, so you learn how to make a graph now. Every day you learn something of it. Okay, so now this graph is not only useful for this experiment, you can use the same graphing technique for some other experiments too. And not only that, if you're doing some other subject, you may need this draw a graph or something. So that's your lab report thing. And then after pasting this thing, over here at the bottom, you can actually start typing in calculation for slope. What's the calculation? G is how much? G is 4 pi square times the slope. The slope is right there, 0.25421. So can you calculate that? G, how much is it? 4 pi square times 0.2521. 0.2521, yeah. Multiply. 4 times pi square. Pi must be from the calculator, not from 3.14. It should be from the calculator. There we are. You know the actual acceleration due to gravity. It should be around there.
9.95.
9.95, slightly on the higher side. 9.8 is expected to be around the answer. But 9.95 looks like a little on the higher end. Obviously, tiny differences of time period can make huge difference. You know why? Because you're not just using time period, you're squaring it. When you square it, things get worse. So if you made a little error in the time period, the time square will show a bigger error. So there are chances of errors. So I can see that the points are not perfectly in a line. Look, this is slightly up. And this one is slightly up as well. So these two are slightly off. Which is like, this is our 0.4 something, and this is a 0.5 something. Those two are slightly off. So maybe we are in a hurry to take somewhere new. So Any questions about it? How to transport Excel to here? Just the very last equation I have written down before precautions on the page, on the paper I gave you, before precautions. Yeah, all you do is just write this. Slope m is equal to 0.2521, and then g is 4 pi squared times 0.2521, and get the answer, and that's over. And what's the unit? What's the unit of g? G is not unit. Force is unit. G, acceleration due to gravity. Huh? Meters per second is for speed or velocity. Meters per second squared. Yeah. Acceleration due to gravity. So when you do is 4 pi squared. So g is 4 pi squared times 0.2521, and that will come out. How much is it? 9.95 meters per second squared. That's the right answer. So you can actually find out the percentage uncertainty or percentage error involved, and you can find out, like, how do you find the error? Taking 9.8 as the.
So on formulas, we used to like the one you're saying that one.
Whatever I said, yeah, that's
Can
it.
we use the base formula?
For the formula, just write the whole thing down.
Right, all of that? Okay.
Because how this last formula comes is what I've shown there. So you can write the whole thing down.
All right, other question. So that other equation part, the 2 squared equals 4 pi squared L over G, we're not using that one at all?
This is what we used to get there.
Okay, so this is how we got some G.
So that's why you start with this and then just write this part. That's the only equation you're going to write. The whole, in fact, the whole simple pendulum experiment is based on that equation. T equal to 2 pi radical L over G. Yeah. All right. If there are no questions, then you're free to go home. Imagine we are all doing all the experiments, both experiments. It will be like taking time.